morning again. It's 11 and we can continue. All right. So at this point, up to this point, we discussing stuff which you already, most of you are familiar, right? Just Newtonian formalism, right? And from this point, we will start moving into, for some of you, a new world, right? And you've never seen like Lagrangian formalism. It's not a rocket science, right? But for most of you, it's new. But before we go into the Lagrangian formalism, we need to review calculus of variations. Why? Because Lagrangian formalism uses tools of calculus of variations. So we will derive here the major formula, right? And then we will just grab it and use it in the Lagrangian formalism, right? With small adjustments, right? Not that significant, right? So I'm sure that at some point you learn calculus of variations in your, one of your maybe calculus classes. Actually, I need to find out where, right? But I remember myself, it was the second year, right, at the university, and we were quite fascinated by this completely different approach, right? Really different from normal calculus, right? It was so new, it was so, you know, refreshing even, right? I remember we were impressed by this. But anyway, right, so let's write the title, Calculus of Variations. And before I write down the goal of calculus of variations and so on, let's look at a couple of examples in order to actually see the goal, right? On sort of on real examples. But first, of course, let me write down the title. So, Calculus of Variations. Right. It's chapter 6. Probably I should write it down also. Chapter 6. Right. And all right. So let me write. So idea of calculus of variations. All right. So let me write idea of. You know what? Calculus of variations. Since I'm going to use it from time to time, let me abbreviate it. It's not universal abbreviation, but COV, calculus of variations. So idea of calculus of variations, right? So basically like a goal. What's the goal of COV? And let's look at a couple of examples, as I said. All right, look at 2 examples. Should I label it number 1? Yeah. Okay, number 1. Let's imagine this situation. So you have plane, right, flat, 2 points. What is the shortest path between these 2 points? Of course, you can say, come on, it's obvious, right? Yeah, it's obvious because we have that situation in our everyday life, right? But we need to develop a tool which can be used to find, to solve problems like this and problems similar to this, right? Some mathematical tools which wouldn't be based on our everyday life experience. Right? Okay, so the shortest path in a plane between 2 points. All right, so should I, yeah. So the shortest path between 2 points in a plane, 2-dimensional situation, right? Okay, so let's draw the situation, right? So let's say x, y, and every time if you have a problem like this, of course, you have a beginning, you have end. End points are fixed, right? You know your beginning, you know where you want to be, and you want to find the shortest path. So the end points are fixed. So let's say this is initial, and this is point 2. Of course, this will be x1, this will be x2, this is y1, y2, right? And we basically need to find the path with the shortest distance, right? Okay, so how should we start it? Let's pick a completely arbitrary path. Completely arbitrary, right? So let's say this is the any path. So pick an arbitrary path. Let's say y as a function of x. Two-dimensional situation, it's basically equation over some arbitrary line. Y is a function of x. And then what? Of course, we need to take infinitesimally short section of this path, right? So let's say ds, right? Of course, which has components dx and dy. And of course, we can write the element of the path ds easily as square root of dx squared plus dy squared. Okay, if this is length of ds, then if we want to calculate the total distance between these 2 points using this line, this path, then of course, I think I use L. Yeah. So the length will be L equals, of course, integral from the first point to the second point. Right now, I don't know which variables of integration I'm going to use, variable of integration, so I just put 1 and 2. And it will be, of course, ds. We need to integrate that. Okay, so now, of course, it will be integral of square root of dx squared plus dy squared, right? Still 1, 2, because right now we still have two variables, x and y. I still haven't made a decision about which variable to use, right? So in order to make a decision, so now I have to pull out of this square root sign either dx or dy. Let's take dx outside, right? And in that case, we will have, all right, L equals integral square root of 1 plus y prime of x squared dx. So in this case, you see, I took dx outside. As a result, I have here dy over dx prime. You see prime. N squared. So now, yeah, we have one variable of integration x. So now I can write from x1 to x2. So that's what we have. Let me frame it like this. And now, again, what's the goal? The goal is to make this, to minimize this, right? We're trying to find the shortest path. So basically, by looking at this, you can say, yeah, we have almost everything. We have endpoints given, right? We have an integrand, except for we don't know the true path. The true path, which makes L minimum. So everything is given except for what is actual correct path, the true path, which is y is a function of x, because right now we just pick an arbitrary path. But of course, we need to find that single unique path, which is going to minimize this distance, right? So basically, we need to develop a tool which can be used to find the true path y as a function of x, which makes this minimum. But of course, we're going to develop a tool which is going to make this stationary. But we will talk about this later. All right, so now let me Right. So here we know everything except the true path. The true path. To make L minimum, to make that distance L, wait, let me just abbreviate, minimum. Right. Okay, so we need a tool. So we need a tool, kind of tool. Of course, we will derive it. But for now, you see what we need. We need to find some, we need to have some procedure which will allow us to find this y, so that in this integral L, so that L is minimum. L is this integral, right? So this L is minimum. Right? There will be situations where you can have to maximize, but in our cases, most of the time, we're going to search for minimum. So that's one example. We're going to finish it. Right? So we will leave it behind for, I don't know, 20 minutes, develop the tool, and then we'll get back to this example. The second example. So what if Fermat principle? So you know, the light travels between points, trying to minimize what? Of course, travel along the path, minimizing time, right? Okay, Fermat principle. All right, Fermat, right? Principle. Basically, again, two-dimensional situation, right? So you have x and y, initial point, final point, right? So you pick some arbitrary path. Okay, let me redraw basically the picture. Again, it will be y, x, point 1, point 2. Again, the same story. You will pick every time you will pick some arbitrary path. Right now it's not, of course, it's not going to minimize time when we set up the problem. Right. Again, you will take ds, right? And so now, instead of minimizing distance, now we are going to minimize time. So now, so tau, I think I label it tau. Yeah, so it will be integral of dt. Right, so basically dt, it's a time to cover this ds, right? So it will be, of course, from 1 to 2, integral of ds divided by v. Simple math. I mean, simple physics. Again, from point 2 to from 1 to 2. All right, ds, we know we can, we already wrote down ds over here. Right, again, if you take dx outside, okay, let me write it. So first, dx squared plus dy squared, right? And divided by, okay, let me write first v. And now, so how can we write v? Of course, we know the index of refraction, which can be a function of x and y in the most general situation. Of course, it is introduced as c, speed of light, divided by the velocity of light, right? So v will be c over n. Right. So we'll plug it. As a result, tau will be equal, 1 over c will be downstairs, so I will take it outside, 1 over c, integral. Now I will take dx outside, like we've done here, I've done there. And so it will be square root of 1 plus y prime of x squared. Then n will be also upstairs. Let me write n as a function of x and y and dx, and divided. That's it, right? C, yeah. So nothing. There's no division. I took C outside already. Right. Okay, so that's the integral in this case. So here we minimize distance. Now we're trying to minimize time. And again, the same story. Everything is known, like what I wrote here, except for the true path, y as a function of x. Right now we picked an arbitrary path, but of course you need to sort of optimize and find the true path, which is going to minimize the travel time. Right. So second example, again, we need a tool, so which can be applied, used to find the true path, and which would guarantee that this, the value of this integral here or there will be minimum, right? So that's the goal of calculus of variation using these examples you can see. And now let me write. So the calculus of variation, sort of like a precise definition of the goal of calculus of variation, is about calculus of variation is about finding extreme values of these integrals, which we are going to call functionals. Right? I will define in a second functionals. Right? Basically, these functionals are quantity presented in an integral form. Right? Okay, so let me write a strict definition of the goal, and then we will start working on the tool which we need to find this true path. Okay, so the calculus of variations is about finding extreme values, as I said, of functionals. Right, so let me take this down. COV, again, calculus of variations, is about finding extreme values Okay, let me write, extreme values. So it can be mean, minimum, can be maximum. Extreme values of functionals. All right. Of functionals. Basically quantities that or quantity that is expressed as an integral. And that is expressed as an integral. Right. And the major difference between functions and functional, on purpose they change the name to the function, but now they added AL, functional, to distinguish between these two mathematical ideas. So in a function, what do we have as inputs? For example, y is a function of x. It's a function. So inputs, x, numbers. Outputs, y, also numbers. So numbers in, numbers out. In the functionals, what do we have? Functionals, like in this case. So what do we have as inputs? You have functions, n as a function of x and y, then y prime, right? So as inputs, we have functions. As an outputs, because these are definite integrals. Okay, I forgot to put the limits from x1 to x2, right? So inputs, functions, outputs, of course, numbers, right? Okay, so and sort of graphically, usually something like this is drawn. Right? So let's say this is y, this is x. Let's say this is initial point, this is the final point, 1 and 2. And so what does it mean? So you take an arbitrary path, for example, this one. And you calculate it, let's say length or time. And let's say you get some number, whatever, 5. Then you will change this path, for example, to this one. But again, endpoints are the same because according to your problem, you have initial and the final point, right? Endpoints are fixed. You just change this path to this one, and you calculate the value of the functional. Let's say now instead of 5, you got 6. Damn it, it's getting bigger. But let's say we want to minimize. So I'm moving in the wrong direction. So you change the direction, and now you'll start looking, for example, you will change your path to this one. Calculate L or tau over that path. And let's say you'll get now 3. Oh, okay, we're getting towards minimum, so it's better, right? So then you'll keep moving now. Let's say you look at this path. Let's say you got, I don't know, 1. Okay, we're still decreasing, so it means you keep moving that way. So you keep probing and probing. Let's say at some point, let's say over this path, not some point, over some path. Let's say you got, I don't know, 0.2. I'm just making it up. And if you pass this path, and your value, the value of L or tau start increasing. So now let's say now here we had, I don't know, as I said, 0.2, and now the next path, it will be, let's say, maybe 0.5. And you see now the value of functional starts growing. So it means that this will be the true path, which is going to minimize. So that tool, which we're going to develop, allows us sort of like to change this path, searching for the minimum, right? So you move this way, okay, it's increasing. Move this way, it's increasing again, okay? So this seems to be like a minimum, right? So that's what calculus of variation does. It just change your path, searching for the minimum value of functional, whatever functional is in your problem, right? Okay, so let me show that. For example, this gives us L minimum, and this path, let's say it's L larger than L minimum. Then again, over here as well, I can say that L is larger than L minimum, right? So that's what calculus of variations does. It allows you to find the path along which a certain functional of your problem is minimum. But of course, in general, we will see when we start deriving that we will be able to guarantee not the minimum value, but a stationary value. So it can be minimum or maximum. But you will see in most of our problems all the time we will have to minimize, right? So we'll have to find the minimum value of something along a path. Right. So that's the introduction into the calculus of variations. So now once you have more or less clear picture, and you should have a clear picture already. We just refreshed it, right? And now let's start deriving the tool, right, which we need to find again the true path making these functionals stationary. Okay, so the title, let's derive what is called the Euler-Lagrange equation. Different pronunciation of Euler, right? Euler, I've heard different. I don't know which one is correct. So I heard this pronunciation, so I'm trying to use that. Okay, so now the title. Okay, I will put a new bullet, and Euler-Lagrange equation. Right. Okay, so let's assume that we have a completely, just completely arbitrary functional. So let me write it. So S. So here we have L. Here we have tau. Let's just call it in general S, which is a function of y, and that is a function of x. Again, the major difference between functionals and functions that in a functional inputs are or in a functionals inputs are functions. Okay, let me write that. Now first let me complete the functional and then I will state that. So integral from some x1 to x2 and some integrand f. Like in this case, f was this square root times n as a function of x and y, so that is f. In this case, f is that square root. Right. So some integrand which can be a function of y, y prime, and x itself, dx. So you see, sometimes you can have y primes. You can have y's, which are functions of x, and you can have x. So I combine them all, y, y prime, x. And we assume that our variable of integration is x. Although we can have sometimes different variable of integrations. I will talk about that when we start looking at examples. Right, so that is a functional. Our functional. And now I will emphasize that inputs are functions, output numbers. All right, inputs are numbers. Wait, inputs are functions. Outputs are numbers. Right. So that's the major difference between function and functionals. In a function, numbers in, numbers out. Here, functions in, a number is out. Okay, so and now let's imagine some completely arbitrary situation, some initial point, final point, right? So let me draw it here. So y, x, and let's say this is point 1, and this is point 2. And again, and some function is given on this in this space, right? Two-dimensional space in this case. So now let's assume. Okay, I will write assume. Yeah, let me use. Okay. So let's assume that y as a function of x is the true path. Let's assume that we know y as a function of x is the true path which is going to minimize our functional s, right? Is the true path. Okay, let me draw this true path using the red color, right? So that is a y as a function of x, true path. Right? Let me maybe emphasize the true path that minimizes s. Okay, now let's construct a variation. Basically, this path, basically these paths are variations of the true one. So now let's construct a variation, or we can call it a wrong path. Now let's construct a variation. A variation. That's why it's called calculus of variation. Let's construct a variation. Basically, a wrong path. And let me call it y capital. Still, as a function of x, right? It's just a wrong path. Okay, let me use some blue color, for example, right? So this is our wrong path, y capital as a function of x. And we're going to construct it in this way. We're going to distort the true path just slightly, right? So we're going to construct it in this way. So we're going to take the true path. Again, it's basically variation of the true path. Slightly change it, slightly distort it. So the true path, right here, and plus, since, as I said, we want to distort it slightly, so let me introduce a small parameter alpha, real, right? Alpha is the real and small parameter. And let's multiply this small parameter by an arbitrary function eta. It can be any but well-behaved function. What does it mean, well-behaved? It means that, yeah, it's continuous, and you can differentiate it as many times as you want. So, well-behaved, good-looking, so whatever adjectives you want to use, right? So, eta of x, and I will emphasize any. It's a key word, any. You will see at some point why. Any well-behaved function. Well-behaved function. Again, it means that it's continuous and you can differentiate it as many times as you want. Okay, what else do we have to impose on our function eta? Very important. It doesn't matter, like in all these examples, which path you take, wrong, correct, true, right? Every time all paths goes through the endpoints. Because you know in your problem, you want to be here and you want to be there. The endpoints are fixed. You cannot change them because in that case you change the problem. You want to solve a particular problem, so it means that endpoints are fixed. Otherwise, it will be different problem, right? So endpoints are fixed. Okay, as a result, so it means that y capital at endpoints. Okay, let me write. So this is x1 and this is x2. This is y1. This is y2. So the value of y capital at x1 must be equal to the value of y small at x1 because they meet at that point. And also at that point, y capital at x2 must be equal to y small at x2. So in order to make that happen, so eta at the endpoints must be equal to 0, right? So value of function eta must be 0 at the endpoints. We have to demand that. And eta at x1 equals to eta at x2 equals 0. All paths must go through the endpoints. All paths must go through the endpoints. They are fixed. Endpoints are fixed. Okay, maybe I will write. So, endpoints are fixed. As I said, otherwise it will be different problem. Okay, so these are preliminary steps. Since I will use it from time to time, let me frame it so that it will be easier for me to spot it. This is the true path, right? Okay, so these are our introduction, and now let's evaluate our functional at the wrong path. Why not, right? So I will basically now this sort of like a stating the problem, and now let's start massaging it. All right, evaluate S along the wrong path, along, okay, a wrong path. You know, although we already stated it, of course, it's the wrong path, along the wrong path. And so now I will need plenty of space. I have to invade this part of the board. Yeah, I don't know how I'm going to survive on this board, this derivation. Okay, we'll see. So evaluate. So it means that S are evaluated along the wrong path. So Y capital, right? So it will be integral, but now instead of Y small, we have Y capitals. Right. So integral from x1 to x2. And you know what, in order to save a little bit of space, let me write f, and I'm not going to write y capital, y prime capital. I will write it immediately in terms of y small and eta. All right, so here we'll have y capital, y prime capital, but I can write immediately, so it will be here y small plus alpha eta, and here we'll have y prime plus alpha eta prime. So it will be, which way? Yeah. Y plus alpha eta, then y prime plus alpha eta prime, and x, right? And dx. So now, what are we going to get if we integrate it through? You can still see it. Yeah, it's visible. Right. So it's an integral over x, definite integral. So upper and lower limits are given, some numbers. So if you integrate it, x will be integrated out. So x will not be left. It will not be here. Of course, y is a function of x also. So everything will disappear except what? Everything will be turned into numbers except what? Except our newly introduced real small parameter alpha. So alpha will survive through this brutal integration. So it will be at the end. There will be some numbers and alpha present. And we haven't imposed any significant restrictions on our alpha, except for its real. And small, yeah, but. So, can we basically now, at this point, can we start treating alpha as the variable? So now we'll get here something, some constants, some bunch of constants, and alpha. So I can write this, that this will be some new function s as a function of alpha. So now I can start treating my alpha as a variable. So now I will have just a normal regular function of alpha. S is a function of alpha. So I'm not going to have any some weird functionals, right? So because we have no idea how we can treat those functionals, how we can find that, how can we minimize them. So far we have no idea about them, not much. But by doing this, by introducing artificially this parameter alpha, now we're basically switching, moving from some weird world of functionals into the regular world of functions. And in this case, it's a function of one variable alpha. We have tons of tools from calculus 1, calculus 2, which can be used to analyze this function. This is probably one of the most important steps. By doing this, by introducing this alpha and analyzing this way, we're switching from the strange world of functionals to a normal, regular world of functions. Okay? So this is probably, in my opinion, one of the crucial pivoted points in this derivation. And then the rest will be regular calculus, right? That have to be applied. That has to be applied. Right. All right. So now let me emphasize on this. So here we have a functional, and this is just a regular function of alpha, regular function of alpha. So we switched. So we switched from functionals to regular functions. Okay, let me put an exclamation mark and happy face. Okay, what else now do we know about this function s, which is the function of alpha? What else happens? Now we have also important piece of information which we need to realize. What happens when alpha equals to 0? When alpha equals to 0, this of course 0, and our wrong path turns into the true path. What happens with our functional when we are on the true path? It becomes minimum, right? That's what we assume, that y as a function of x is the true path which minimizes s. So if when alpha equals to 0, y capital equals to y small, and s is minimum. So at alpha equals to 0, our functional is minimum. Our function, in this case, it's a function. We switch to function. Our function reaches minimum value. So now, on top of that, of the fact that we switch to normal functions, now we also know one additional piece of information, that at alpha equals 0, our function is minimum. Right. Okay, so moreover, when alpha equals to 0, y capital equals to y small, and s reaches minimum. When, okay, let me, alpha equals to 0 and s reaches minimum value. So now this statement will allow us to dive deeper and get what we wanted. So first we made a transition to a normal functions, and now this piece of information will allow us to continue through the derivation. Right. So, and we know what how we can find the first step in a search for minimum points. First, you need to find the stationary points, right? You need to first differentiate function with respect to the variable, right, and equate it to 0. It's a first step, right? So, ds over d alpha when alpha equals 0 equals to 0, right? Stationary point. Oops.
So the reasoning behind actually having this like alpha parameter is like we're kind of guessing at a wrong path, and with this alpha parameter, we can kind of constrain our solution such that it'll actually be the correct path. Is that kind of?
Yeah. So when alpha equals to 0, as I explained, yeah, alpha equals 0, so this disappears, and with that parameter, our wrong path becomes the true path. And of course, the functional is minimum, and of course, since we're getting this function out of the functional, of course, the function will be also minimum. Right? Yeah, that's correct statement, absolutely. Right. Okay, and as the first step of to search for minimum points, of course, you need to search for stationary points. So let's use it. Right. So a search. Oops. Okay, let me just write for stationary points. For stationary points. Right. Okay. So as a result, okay, let me sort of jump ahead. So we're using conditions for stationary points, right? Although this goes much deeper, it tells us that the value of s will be minimum. But what we use the stationary condition. And now using this stationary condition, we're going to derive the tool which we need, right? And as a result, that tool which will be derived can only guarantee that your functional is going to reach it can be stationary. It cannot guarantee that will be a minimum. So it can be a minimum or can be a maximum, right? Because again, stationary conditions cannot guarantee that guarantee that it will be a minimum point. It can be minimum and maximum, right? So in order to prove that the value of the functional is going to be minimum, you have to do some additional stuff. We're not going to do that. So every time in calculus of variations, we use this tool which guarantees only the stationary value. That's why I wrote here extreme values, min, max, right, of functionals. Okay, so now let's differentiate our functional. Let's differentiate along the wrong path, right? And so in order to differentiate integral, let's recall Leibniz rule. I remember it was, I think, in the freshman year, when I was in freshman year, I remember I was practicing, we had to derive everything. So we derived this Leibniz rule, how to differentiate an integral, where the upper limit can be a function of x, lower limit can be a function of x, and integrand can be a function of x. So let me just write down that Leibniz rule, and then we will apply it for our particular case, right? Okay, so sort of small digression. So recall Leibniz. Okay, I don't trust Leibniz. I think that was the correct spelling. No, wrong. Z at the end, just Z. Right, Leibniz rule. Right. So what does it tell us? So if you have d over dx out of some integral, which is a function of lower limit as a function of x, a as a function of x, upper limit b as a function of x, then integrand, which we wrote it, f, which is a function of x, and alpha. Okay, I need to use my notes more often. So instead of x, I use alpha. So let me change also. Since we are going to here integrate or differentiate with respect to alpha, let me also use here instead of x as alpha. Again, what I started writing, it's not wrong at all. All right. So in order just to be consistent, all right. So let me change to alpha since I haven't moved that far. Alpha, and right. So it will be alpha, right, and dx. Okay, so according to that rule, first you need to differentiate the upper limit with respect to alpha, db alpha with respect to alpha, then multiply it by the value of the integrand evaluated at the upper limit, f of b, and alpha, then minus the same with the lower limit, minus dA over d alpha f a alpha, and then plus integral over partial derivative of f. So plus integral from x1 to the limits still. So partial derivative of f with respect to alpha, right, and d Okay, so now in our case, let me sort of frame it. In our case, upper limit number, upper limit, lower limit is number, right? So this and this will be 0. So we just need to differentiate with respect to alpha, because here that's what we do, ds over d alpha. So we'll have to differentiate with respect to alpha integrand and equate it to 0. So in our case, so it will be ds over d alpha will be equal integral from x1 to x2, right? So partial derivative. Should I? Yeah, let me write first df over d alpha and f. Again, we're integrating, evaluating over this y capital. So let me write y capital here. Y prime and x, right? So now I just combine. This is y capital, this is y prime capital, x, dx, right? Dx. Dx. Okay, so now just using simple rules of differentiation, we can get, so it will be integral from x1 to x2. Let me open the square bracket. So it will be df over dy capital, then partial derivative of y capital with respect to alpha, right? This complex function. Then plus partial derivative of f with respect to y prime and dy prime over d alpha and dx. So the easiest part, probably dy capital over d alpha. So dy capital over d alpha, again, partial derivative. It will be eta, right? That's why I framed it, because I knew that at some point I would have to search for that. So dy capital over dy alpha, so just eta. So this is just eta as a function of x. Then this, if you differentiate this with, if you take a prime, right? Prime. So dy prime over d alpha, again, it's a partial derivative, so you'll get only eta prime. Eta prime as a function of x. It's a derivative with respect to x prime. Okay, so now this dx over df over dy prime. Okay, so now let me take care of this term over here. All right, so I hope I can squeeze it. All right, so df over dy capital. So I can write it like this: df over dy small, and then dy small over dy capital. All right. So now dy capital, again, partial derivative with respect to dy small over dy capital. Right. Again, look at this. Y small with respect to y capital, you will get 1 partial derivative. Right. So it will be 1. So this is just 1. As a result, this is equal to the partial derivative of f with respect to y. So this is df over dy small. And very similar, this will be df over dy small. Right. So here it's exactly the same. So this will be equal to partial derivative of f with respect to y prime. Yeah, y prime. Okay, so now let's rewrite it over there with all these replacements. All right. Yeah, I think I can erase this. Okay, up to this point, I still need probably try to keep the picture as much as I can, and this variation. Okay, so let's rewrite it. So it will be equal to integral from x1 to x2. This is okay, df over dy eta as a function of x, then plus this is df over dy prime eta prime as a function of x and dx. Okay, almost everything looks great except for eta prime. Let's try to get rid of that prime in the second term. Right? So let's take care of that prime. Right? So in order to do that, of course, we can integrate by parts the second integral. Right? So let's take care of that here. So it's integral of df over dy prime eta prime dx. Of course, it will be equal just by parts. So it will be df over dy prime eta, right, and limits x1, x2 minus integral from x1 to x2, and now it will be eta as a function of x, and we will have d over dx, partial derivative of f with respect to y prime dx. Prime, it's a d over dx. So here now we have function eta without derivation, and now we have to differentiate d over d prime with respect to x. Okay, so what's the value of this? Eta, it's an arbitrary function, and we demanded this. The value of that function at the end points must be 0. So eta at x2 0, and eta at x1 is 0. So that is 0. So let me dump this So this is 0, since eta at x1 equals to eta at x2 equals to 0. So as a result, we have only that integral, and now we have eta here, so we can bring it back to this expression, and eta and this eta can be factored out. Right. So now let me continue this. It will be integral from x1 to x2. So first I will write this partial derivative of f with respect to y. Then eta will factor out. So that's why I didn't write this eta. So now let me write this. So it will be minus d over dx, df over dy prime over here. So it will be minus d over dx, partial derivative of f with respect to y prime, and now eta. Eta here, eta there. So eta as a function of x, dx. Whew. And again, so what? We started with dx over d alpha, all right? From ds over d alpha. And this ds over d alpha is 0. Right? So now we need to look at this carefully, right? So this part. Okay, let me show that I'm going to move over here. I mean, get the conclusions out of that expression. Right. So obviously, you see that what we need to get. We need to take this bracket, extract it, and call it 0, right? Because it equals to 0, but which magic words do we have to pronounce or say first before we can extract that bracket and call it 0, and that will be our Euler-Lagrange equation? From the mathematical point of view, this must be justified, this extraction of that bracket from that integral. Why can we take this bracket and call it 0? And the key word is, you see what I wrote? I even capitalize. Our function eta, which is over there, you see, just outside of the bracket, our function eta is any, a well-behaved function, but still, key word is any. It can be sine, it can be cosine, it can be tangent, it can be exponential, it can be basically any function, of course, if it satisfies this and well-behaved. So if that must be true for any eta, it means that this can be correct only when this bracket is 0. So right now, the key word is any, right? So it must be true. It must be equal to 0 in any, for any eta, so it means that that bracket must be equal to 0. Right? So, okay, let me write, since it must be 0 for any eta as a function of x, again, that I'm analyzing this, right? For any, then where we can extract that. So we can write, so partial derivative of function f with respect to y minus d over dx out of partial derivative of f with respect to y prime equals to 0. So this is the tool. This is Euler-Lagrange equation. So let me frame it. It's a second-order differential equation. What is an output of this differential equation, second order? It's a function eta. Oh, you ate, damn it. I've been pronouncing eta so much. So function y as a function of x, which is the true path. So the output of this is the true path to the true love, right? Which is y as a function of x. Right. So that is the tool. Okay, so okay, let me write. So this is our tool. This is the tool, which allows us to find the true path, which is going to make, okay, and now I have to again emphasize on this. This condition is not going to guarantee that our integrand s reaches minimum. It can guarantee that it will be stationary. So it can be mean, can be max. But in all the problems which we are going to discuss, it is going to reach minimum value, right? Because again, we just use the stationary condition for stationary points. So that equation cannot guarantee that we are going to reach functional is going to reach minimum. No, it can be minimum, it can be maximum. There are some situations where, I know, if you want to calculate, if you deal with money, with profit, of course you don't want to minimize your profit, right? Of course you want to maximize. So sometimes there are situations where you have to maximize something, right? You might want to minimize your expenses, right? Okay, so this is the Euler-Lagrange equation, and of course when we get to Lagrangian formalism, this equation will be reused. We will slightly adjust it, and that will be our Lagrange equation. Right. Okay, let me check if I mention everything. Let me quickly. Right. Yes, so now what's the procedure? How we can address problems of this type? So first of all, you need to state the problem, like we stated those two examples at the very beginning, right? The shortest distance between 2 points, or Fermat principle. First, you need to write that those integrals, which we call now functionals, first write them down. Then inside of the functional, that integrand, that's what function f is. That's why now I regret that I don't have that original functional, right? You remember we had s, right? And that function f, you have your notes, right? You can see, you can look. That function f is the integrand in that functional. So write down that integral, which is functional. Look inside of the integral. That function f is an integrand. Extract it from there and plug it into this Euler-Lagrange equation, f, and start differentiating. First you differentiate, and then of course you will start integrating. Once you solve this equation, once you integrate it twice, you will get the true path, which is going to make your functional stationary. But again, most of the time it will be minimization. Okay, so that's the procedure again. And now let's finish our first example, which we stated, and I promised that we're going to look at that. Let's look at that example, finding the shortest path between 2 points in a plane, Okay, so now we derived, so I can erase it, and maybe I will be able to finish, although I doubt. So we're going to look at this example. Next class, we will look at Brachistochrone example, and then I will state another problem, right? But you will finish it in your homework, right? And this will be the end of this chapter 6. It's reasonably short. It's just a review of calculus of variations, right? And then Lagrangian formalism. So next week, definitely we will start discussing Lagrangian formalism. So back to our example. Right, so let me write back to the shortest path between 2 points. Path between 2 points. So basically, this is an example. Probably I should have written. So it's an example, right? So we already set up the problem. Right? You have in your notes, I have in mine, right? So you remember we had a functional L. It was equal to the integral from x1 to x2 and the square root of 1 plus y prime of x squared dx. And again, the situation was this. So y, x, this is 1, this is 2, right? And we picked an arbitrary path. This is ds, which is dx, dy as components, right? So we stated the problem. So now we need to find our function f, which is, as I said, just an integrand. So this is our f. So that is our f, which is usually a function of y prime at x. Right? So now that is the function, shoved it into the Euler-Lagrange equation and massage it. Right? Put it in a Euler-Lagrange equation, EL. Right? Okay, so now let me rewrite it. So it will be df over dy minus d over dx. And I'm emphasizing, your variable of or your independent variable is here, d over dx. Here, this y prime and this y dependent variable, right? Independent over here in d over dx in the second term. Right. You will understand next class, because this class I most likely I wouldn't be able to get to that point, right? But you will understand why I emphasize on that. This is dependent, that is independent variable. All right, so df over dy prime equals to 0. Right. So let me say that this is independent variable. Okay, first of all, df over dy. Our function f doesn't depend on y. It depends on y prime. Again, you see we're looking at the partial derivatives. So immediately df over dy is 0, and so this is immediately is 0, right? So df over dy equals 0. As a result, d over dx, df over dy prime equals 0. Warning, especially at the very beginning, plenty of students did this in homework, this silly mistake. They differentiated this function. Of course, yeah, you can differentiate df over dy prime, you will get the function, and then they differentiate it with respect to x. As a result, yeah, they got the second order differential equation. It's not wrong, but then they would stare at that second order differential equation without knowing what to do. You don't have to differentiate this, because you can see immediately, since the derivative equals to 0, this function is constant. df over dy prime is constant. It happens almost still occasionally with some students, right? And then they sent me email, what to do? This differential equation looks crazy. Yeah, because you've done an unnecessary thing, right? Which is not needed, right? So in this case, immediately, the nature give you integrated for you, did the first integration for you, right? So don't go into that math. So since this is 0, the first integration automatic, right? So you'll get df over dy prime equals constant. Don't differentiate this with respect to x, right? Okay, so now as a result, df over dy prime, df over dy prime, so let's differentiate it. Oh, so it will be 1 over 2, then this will go downstairs, 1 plus y prime of x squared, all right? Then we have to differentiate this again with respect to y prime, partial derivative. So it will be times 2y prime, and it is equal to this constant. Right? So 2 goes, and we have this. So let's, of course, square it. Just a little bit left. Let me just quickly do it. So, of course, you will get y prime squared divided by 1 plus y prime squared equals 2. And now I think I will introduce the constant. Okay, C. So I call this constant, labeled it, I call this constant C. Right. Okay, so of course you can move terms around. So you will get 1 minus C. 1, really? 1 minus, how come? Ah, yeah, it's good. Right. Y prime squared equals C plus C y prime squared. So we can move terms around. All right, so it will be y prime squared, 1 minus C equals to C, right? So y prime equals to square root of C, 1 minus C. Of course, we can relabel the constant. Let's call it M. Right. So as a result, now the second integration, y as a function of x, will be mx in plus the second constant of integration. Again, m comes from this automatic integration, and now b from this second integration. So it's an equation of a straight line. Right. So we knew it from the very beginning, using based on our everyday experience, and now, yeah, we develop mathematical tool which gives us the same answers. Okay, guys, so that's it, right, for today. As I said, next class we will again look at the example Brachistochrone problem, minimizing time. Then we will try to minimize area, and then chapter 7, Lagrangian formalism. Okay, guys, so let's call it a day. If you have any questions, go ahead. I will move myself to this side.
Higher in the sky, the